Today I'm going to demonstrate in a live session where I attach a Nucleo board into the USB of a Linux machine. And the purpose of this demonstration is to show the feature of Parasoft hardware-based unit testing. I have a picture of that here. This is a Linux machine and I attach through the USB port a Nucleo G071RB microcontroller. And you can see in my screen here that right now it is loading the Blinky example program. Now below here in my terminal, I am logged in into the Linux machine, which is an Ubuntu 22.04. And when I attach the USB to the port of the Linux machine, it enumerated this endpoint here. And you can also see this actual endpoint name if you do uh, this command here. So when I attached the USB port, it was detected by the kernel, and then a serial endpoint was assigned to it via the special file system /dev. This is just in case uh, it will be hard to identify the associated serial connection endpoint, and it's only why you need to do this logging into the Linux kernel messages. Okay, so anyhow, it's now enumerated there, and the firmware running here is a bare bones Blinky project. If I go to testing folder here, the there's another firmware here, this one that I saved a while ago. This firmware was the one that is instrumented by Parasoft tool using the STM32 Cube IDE. I extracted this firmware a while ago so that I can reuse it very quickly for this demo. I extracted it from the target board. So to clarify, the firmware that is running now in the blinking microcontroller is this one. This is a basic Hello World demonstration without Parasoft instrumentation. So there's nothing to be read or it's not transmitting in a serial communication right now. So in fact, if we type minicom and will not be receiving anything from the serial port. It's just a Blinky application. Okay. So to simplify this demo, I'm going to load the instrumented binary that was built in another session using the IDE. This one, I'm going to load this firmware f1.bin. I'm going to write it, and this will be the command. So OpenOCD is an Ubuntu Linux utility tool that allows us to read and write firmwares from an attached target board. So I'm using a Nucleo 32G0 family, so I have to specify this target configuration. This is already built in when you install OpenOCD Ubuntu command line tool. So everything here is cut and paste except for the actual file name of the firmware, which is this one. So we're going to write this firmware into the target board. And this address here is a fixed address for not STM32 flash memory. So I'm going to press enter now. So we are basically erasing the Blinky application and writing it with the new instrumented binary from Parasoft. So this instrumented binary is a different application. Now I'm going to press enter. So it's written now, and you will notice that there is no more blinking lead here because this is now a different application. This application is the instrumented binary by Parasoft, and after loading it, it executed. And in fact, if we try type to type minicom, okay, this is the last byte that's been transmitted through serial port. Okay, so if we try to type minicom, okay, and I'm going to press the reset button. I think it's B2 of the microcontroller to trigger it to restart the application from the very beginning to reboot the microcontroller. So you can see I'm pressing the reset button now here. So upon reset, the unit test has executed and transmitted through serial communication and received by the Minicom application here. Let me exit now. But sad to say, Minicom will write the raw data, right? There is, instead of Minicom, there is a Parasoft provided serial communication tool, just like Minicom, but it understood the byte format that is transmitted. And that utility tool is um, called the listener. And if you install the Parasoft utility, you will find this listener process in this path here. It is available in Windows or Linux installation. So the listener process is in my path now. So I will run the listener v, vrmd, and then but before I do that, um, you have to create a symlink because the listener does not know the enumerated serial communication endpoint, which is dev tty. So it's not aware of this, rightfully so, because this could be anything, right? The Linux kernel could assign any endpoint, and this is arbitrary. So what happens is the Parasoft listener listens to TTY as a number follows that. But if you type TTY, there are already assigned numbers there. So to be safe, I'm going to create a symlink. And in fact, I already did that here. Div TTY as 14344. Okay, it's not yet there. So I will create a symlink now. um, sudo sudo ln sf div tty ecm0, and the symlink would be dev tty s. Okay, so let's review. So the parse of tool, we will tell it to read from this serial port here, which is a symlink to this uh, system generated enumeration of the attached board. So I'll type the listener command now, listener v rm, v for verbose, d, and then what follows is a number which is one higher than the number here. Since this is 14344, then we'll type 14345. So it's always one higher than. Okay, so it is pointing now to this endpoint here. And follows is the well-known, of course, serial setting parameters, which everybody knows. Um, in this demo, I coded the firmware and in the UART initialization to have these following serial settings. 15 200, and no parity 18. So, okay, this is the settings. This is very well-known serial parameters. And for parity, no stop bit and 8 data bits. The transmitter process here is the firmware running in the board should also have the same serial settings. Otherwise, a slight mismatch, for example, in the parity, will result in a failure to receive data or receive data partially, and there will be truncation error messages. Okay. Now, we are receiving a streaming data just like Minicom, but we're going to write this received data into two files. Okay, two files. The first file is for the test log data. The second file is for the coverage log data. So the way to identify that files is through channel number, CN, and then there's a fixed number, 1B hex, and we should write is to results dot test log. The other one would be identified by 2B channel number, results dot coverage log. So in conclusion, just like you saw Manicom a while ago, where Manicom receives a stream of bytes scrolling in on the terminal, the listener process is just like Manicom. It will receive similar data when I press the reset button, and then it will split the received data into two files. One is the test log file, and the one is the coverage log file. Now I will now press the reset button so that the firmware will reinitialize and re-execute the test cases. But first I'll press enter here. So now it's listening. I'll press the reset button now, and it received the testing has executed, received the coverage and test log data here, and there will be two files here, results, okay, coverage log and test log. Okay. Um, yep. As also a while ago, I have created the same uh, test log here an hour ago, a few moments ago, and they should be binary equivalents. If we diff CPP test results clog to results clog, they should be the same. So this is deterministic. Every run it is um, bit by bit equivalent. Okay, test results are deterministic to the bit level. So even if you execute it again, it should give you the same exact binary of the test log and coverage logs. So I hope that this short demonstration where you see an actual board attached and extracting the test and coverage the data has been helpful. But before saying goodbye, let me flash again back to the Blinky. Okay, let me flash it again. Okay, right. So Blinky firmware bin. So I'm flashing again to a new firmware, the Blinky one, and we should be blinking now. And then we're back to the Blinky program as shown by the board here now blinking. And as you know, this one is not the instrumented binary. It is just an ordinary application blinking. By the way, this binary here is not an ELF file. So this is a raw bytes extracted from the flash memory of the board. So you cannot flash. This is not the same as an ELF file. Okay, an ELF file is much bigger than this. This is not an ELF file. This is an actual byte extracted from the flash memory of the target. Um, okay, just to prove what I'm trying to say is that is the Blinky program. But if you go to where I created this project, where the Blinky is here, and there's an ELF file here, C, and then you'll notice that this is the size of the L file, whereas the Blinky is this one. So they are not the same, right? So they do not have the same format. In fact, if you type the format of the GPIO, it will be detected as an ELF32 executable, whereas this one is just a data. So that's it, guys. So I'm just trying to show you that I'm still trying to find a way to flash an ELF file through the command line as well for now. But right now, I'm just doing it through this bin file, which I extracted using the read, and I rewrite again using the write command.